In today's lesson, we're going to learn about relations. We'll discuss finite relations and infinite relations. We'll learn how to represent relations using the roster method, using a map, and using a graph. And we'll also talk about the domain and range of relations. Let's start with the definition of a relation. A relation between two sets is a collection of ordered pairs containing one object from each set. The simplest definition of a relation is that a relation is just a collection of ordered pairs. It's as simple as that. So let's look at a couple examples of relations. Again, a relation is just a collection or a set of ordered pairs. So we're using our set notation here. So this is a relation because it's a collection of some ordered pairs. Here, this relation shows the relationship between x values and their corresponding y values. In your relation, you could have 5 ordered pairs like we have here. You could have 10 ordered pairs. You could have infinitely many ordered pairs. To write a relation, the order that you list the ordered pairs does not matter. So we could jumble up these ordered pairs in any order and it would still be correct. Here's a different example of a relation. This is an example of a relation between students and their birthday month. First, we're going to talk about finite relations. Finite relations will have a limited number of ordered pairs. These are examples of finite relations. Later on, we'll discuss infinite relations, which have infinitely many ordered pairs. We can represent finite relations in 3 different ways. The first way is the roster method. When you're describing a set using the roster method, we draw these curly brackets, and then we just list each ordered pair and then separate them with a comma. So these examples of relations have been represented using the roster method. We can also represent finite relations using a map, which we'll discuss down below, and a graph, which we'll discuss on the next page. Let's practice using a map to represent a relation. So we're given this relation right here, and we want to represent it using a map. Notice, as written, this relation is written using the roster method. We have those curly brackets, and then each ordered pair is listed separated with a comma. That's the roster method, but now we're moving on to a map. So when we are using a map to represent a relation, we start by drawing a box, and in that box, we're going to put the x values. Now, with maps, you can draw a box, you could also draw an oval. In fact, any sort of long shape will do. So let's go ahead and look at our relation and identify our x values. One of our x values is Bob, so we'll list Bob. Then we've got John. Then we've got Bill. And then we've got Mark. Next, we draw a second box, and in this second box, we list the y values. So let's see, we'll list 18 and 20, 21. So we've already written down 20, so when we're listing our y values in our map here, we don't repeat. So we only list the 20 once. Same with x values. If there were repeated x values, we would only list them once. Also, the order you list the x values does not matter. You could mix up these x values in any order, and the order you list the y values does not matter. Next, with a map, we'll use an arrow or a line to connect the x value to the corresponding y value. So Bob corresponds to the number 18, so we draw an arrow from Bob to 18. John corresponds to 20, so we draw an arrow from John to 20. Bill corresponds to 21, so we connect Bill to 21. And Mark corresponds to the number 20, so we connect Mark to 20. And this is our completed map. So these are just 2 different visual ways of representing a relation. This is the roster method, and this is a map. Next, let's discuss the domain and the range. The domain of a relation is the set of all first elements, also known as the x values or the inputs, in the ordered pairs of the relation. When stating the domain or the range of a finite relation, we use the roster method. Again, when you're writing a set using the roster method, you start with these curly brackets, and then you list the elements and separate your elements with commas. When you're describing relations, the elements are ordered pairs, so you would be putting ordered pairs here. When you're describing a domain, the elements are the x values, so you'd be putting just the x values and separating them with commas. So when we're asked to describe the domain for this relation, we should use the roster method, and we just start with these curly brackets, and then for the domain, we list the x values and separate them with a comma. We could have also obtained the domain from our map by just copying down these x values right here. The range of a relation is the set of all second elements, also known as the y values in the ordered pairs of the relation. Again, when we're describing the domain or the range of a finite relation, we use the roster method. So we'll start with these squiggly brackets, and then for the range, we'll list the y values and separate them with a comma. Let's see, we've got 18, 20, 21. We said with the map, we never repeat x values. We also never repeat y values. It's the same with the domain and the range. We see that 20 appears twice. We only list it once when describing our range. We could also have obtained our range by looking at the map here and just copying down the y values. So I've added here that the x values are also known as the domain and the y values are also known as the range. So we've been looking at finite relations. We've learned how to represent finite relations using the roster method and also using a map. On the next page, we're going to see the third way we can represent finite relations, which is using a graph. For this example, we're given this relation here, and we're going to represent the relation using a map and also a graph. This is another example of a finite relation since it has only a limited number of ordered pairs. There aren't infinitely many ordered pairs. This relation right here is written using the roster method since we have these curly brackets and each ordered pair is listed and separated with a comma. First, let's use a map to represent the relation. We start by drawing some sort of long shape. I've drawn an oval here, and then we list the x values. And remember, if there are any repeated x values, we only list them once when drawing our map. So the next x value is a 1, but we've already listed that x value right here, so we don't repeat it. Next, I've drawn another oval, and in this second oval, we list the y values. And we don't want to repeat any y values. I see a 6 here, but we've already listed 6 as a y value, so we don't repeat it. And the last y value is 4. Now we draw our connections. So we'll connect -2 to 6, -1 to -2, 0 to 0, 1 to -5, 3 to 6, and 1 to 4. Now the order that you listed the x values here doesn't matter, and you could also switch around the order that you listed the y values. So this is a map. To represent the relation as a graph, we just want to go ahead and plot each ordered pair. So I'll start by plotting the ordered pair -2, 6. Then I'll plot the ordered pair -1, -2, and then I'll go ahead and plot the other 4 ordered pairs. So here we've represented the relation using a graph. And you don't have to label each of your ordered pairs, I just did that for clarity. So we see that any finite relation can be represented in 3 different ways, using the roster method, using a map, and using a graph. Next, let's describe the domain and the range of our relation. And remember, with finite relations, when we're describing the domain and the range, we use the roster method. For the domain, we simply list the x values. So we draw the curly brackets, and then we list our x values and separate them with a comma, making sure not to repeat any x values. We can identify the x values by looking up here. They would be -2, -1, 0, 1, 3, and we've already listed 1, so we don't repeat it. We could have also determined the domain by looking at this map and by copying down these x values. We could have also determined the domain by looking at the graph and by copying down the x value of each ordered pair, which I've drawn in green. Next, let's write the range, again using the roster method. So we'll draw our curly brackets, and then for the range we list the y values and separate them with a comma. So the y values would be 6, -2, 0, -5. We've already listed 6, so we don't repeat it, and 4. We could also have obtained the range by looking at our map and listing these y values here. And we could also have obtained the range by looking at the y-coordinate of each ordered pair on our graph. And again, for the domain or the range, the order that you list the numbers does not matter. On this last page, we're going to discuss infinite relations. Infinite relations are relations that have infinitely many ordered pairs. If we look back for a minute, we learned that for finite relations, we can use the roster method, a map, or a graph. The roster method does not work for infinite relations because you could never list infinitely many ordered pairs. A map also does not work for infinite relations because you could never list infinitely many x values and infinitely many y values. So for infinite relations, we don't use the roster method or a map, but we can use a graph. So one way to represent infinite relations is using a graph. And the second way to represent infinite relations is using an equation. We'll see examples of this next. To start, this graph represents an infinite relation. An infinite relation is just a collection of infinitely many ordered pairs. You can picture there are infinitely many points along this solid line here. You can also represent this infinite relation using an equation. Now, you don't have to worry about coming up with this equation. For this lesson, you just need to know that it's possible to represent infinite relations using an equation like this. Now, how do we describe the domain and the range of an infinite relation? Let's look back for a minute. With finite relations, we described the domain and the range using the roster method. But this will not work with infinite relations because you could never list infinitely many x values for your domain, and you could never list infinitely many y values for your range. So when describing the domain or the range of an infinite relation, we can use interval notation or set builder notation. We'll look at both of these next. So remember, the domain refers to the x values. If we want to describe the domain of this graph, we're supposed to describe all of the x values that lie on this graph. With interval notation, we list the lowest x value, and then we put a comma, and then we list the highest x value. Sometimes it can be helpful when you're looking for the domain to grab 2 sheets of paper like this and to block your graph from the left and the right, like we see here. Our whole graph fits in between these 2 pink pieces of paper. Now let's identify our lowest x value. Since the x-axis runs from left to right, our lowest x value will be the x value furthest to the left, which is this point here. And the x value of this point is 2. So the lowest x value, or the x value furthest to the left on our graph, is 2. So for our interval notation, we list the 2. Remember, with interval notation, parentheses mean you're not including that endpoint, and brackets mean you are including that endpoint. Since 2 is an actual valid x value on our graph, we want to include it, so we'll use brackets. Then we put a comma, and we list our highest x value. Since the x-axis runs from left to right, the highest x value is going to be the x value furthest right. This point here is furthest right on our graph, and the corresponding x value is 6. So we'll put a 6 right here, and again, we want to include that, so we'll use a bracket. We can also represent the domain using set builder notation. We learned set builder notation in chapter 1.4. For set builder notation, you start by drawing this general outline. So for set builder notation, we want to write an inequality to represent the domain or the x values on our graph. Again, we see that all of the x values on our graph range from 2 to 6. So the inequality that we can write to represent the x values on our graph is x is between 2 and 6. Next, let's discuss the range. The range refers to the y values. Now, again, there are infinitely many points along this graph. So there are infinitely many y values. So to describe the infinitely many y values, we again can use either interval notation or set builder notation. Let's start with interval notation. For interval notation, we list the endpoints like we did up here. Here we listed the lowest x value and the highest x value. For the range, we'll list the lowest y value and then the highest y value. We can put our paper blockers this way. Our entire graph fits within this window. So let's start by identifying the lowest y value on our graph. Since our y-axis runs up and down, the lowest y value will simply be the lowest point on the graph, which is right here. And let's see, the y value of that point is -2. So for the range, we start with the lowest y value. And since that's an actual point on our graph, we want to include it, so we use a bracket. Then we list the highest y value. The highest y value will be the point that's furthest up on your graph, which is right here. And the y value of this highest point is 4. So we'll put a 4 and then again a bracket. So this interval notation says that our y values, or our range, goes between -2 and +4. To describe the range using set builder notation, we start with this general outline. Notice since we're talking about the range, we put a y here instead of an x. And then we're going to use an inequality to describe the y values. Again, the y values range from -2 up to +4. So we can describe the y values using this inequality. Before we move on to the next example, I just want to make sure that we fully understand what these notations mean in terms of the domain and the range. So for the domain, for example, this notation means that the x values of our graph include every real number between the endpoints 2 and 6. This set builder notation means the same thing. This means that the x values on our graph take on every real number between the endpoints 2 and 6. So for her domain, the x values on our graph take on every real number between 2 and 6. So you could picture, maybe this is 2.1 on the x-axis. Well, there will be a corresponding point on your graph that has an x-coordinate of 2.1. Maybe this is 2.2 on the x-axis. Well, there will be a corresponding point on your graph with an x value of 2.2. Maybe this point right here is 2.5789. Well, there will be a corresponding point on the graph with an x value of 2.5789. So hopefully you can see for the domain, notations like these mean that the x values on your graph include every real number between the endpoints 2 and 6. For the range, this notation means that the y values on your graph include every real number between -2 and 4. This notation means the exact same thing. So if we quickly look back at the graph we made on the previous page, this was a finite relation because there were only 6 ordered pairs. There were not infinitely many ordered pairs. So with finite relations like these, we never use interval notation or set builder notation. Instead, we use the roster method where we just list the x values and the y values and separate them with a comma. For the domain, it looks like the x values are between the endpoints -2 and 3. So why couldn't we use interval notation for the domain here? This says that the x values are between -2 and 3. The reason we cannot use interval notation for finite relations like these is because, again, this notation means that the x values on your graph include every single real number between -2 and 3. There are infinitely many real numbers between -2 and 3, but there aren't infinitely many x values on our graph. There are only 6 x values on our graph. So we cannot use interval notation here to describe our domain. Same with the range. It looks like for our range, the lowest y value is -5 and the highest y value is 6. So you might ask, can we use this interval notation to describe the range? No, we can't, because this interval notation says that the y values on your graph take on every real number between -5 and +6. The y values on our graph do not include every real number between -5 and 6. The y values on our graph only include these 6 real numbers. So we would not use interval notation for the range. Let's look at one last example. If you see a graph that's connected by solid lines, that will be an infinite relation because there are infinitely many ordered pairs along a solid line like this. Let's start by identifying the domain. For the domain, again, we're looking for the x values. And for interval notation, we list the lowest x value and then the highest x value. Let's look at the previous graph for just a second. Remember, the x-axis runs from left to right. So your lowest x value will be the point furthest left, and your highest x value will be the point furthest right on the graph. When determining the domain, we put our blockers on the left and the right, and our entire graph fit in this window. So we could see the leftmost x value or the lowest x value and the rightmost or the highest x value. But for this graph, we can't block our graph from the left and the right because this graph keeps going off to the left and it also keeps going off to the right. So I'm going to remove these blockers. To help us visualize the domain of our graph, I've drawn a very rough sketch of a zoomed out version of the graph from the previous page. When we're looking for the domain, we focus on the x-axis since the domain refers to the x values. Let's pick a couple points on our graph and look at the corresponding x values of those points. The x value of this point here might be -4. The x value of this point here might be around -8. The x value of this point here might be -15. Hopefully you're starting to see that as the graph moves further and further to the left, the x value of those points keep getting more and more negative. And this arrow indicates that the graph continues indefinitely to the left, so our x values are going to move towards -infinity. So our lowest x value is -infinity. And remember, with interval notation, we always use parentheses next to positive or negative infinity. Let's examine a few more points to find the highest x value on our graph. The x value of this point might be around +4. The x value of this point might be around 8. And the x value of this point might be around 15. Notice as our graph extends indefinitely to the right, the x values keep getting larger and larger. This arrow indicates that our graph continues indefinitely to the right, so our highest x value will be +infinity. When you're determining the domain, if your graph has an arrow going off to the left, that means your lowest x value will be -infinity. And if your graph has an arrow going off to the right, that means your highest x value will be +infinity. To represent the domain using set builder notation, we start with that general outline, which looks like this, and then in here we write an inequality to describe the domain. For this graph, the inequality we could use for the domain would be that x is between positive and -infinity. Notice here we used less than or equal to symbols because we wanted to include those endpoints. But infinity is viewed as being unreachable, so you can't actually reach or include those endpoints, so we use less than symbols instead of less than or equal to symbols. Okay, let's end with the range, which again describes the y values. So for interval notation, we want to list the lowest and the highest y value. If we look at our previous graph, the y-axis runs up and down. So to describe the lowest y value, you find the lowest point on your graph, And to describe the highest y value, you list the highest point on the graph. You can use your blockers to block the graph from the bottom and the top to enclose your graph in a window where you can see the lowest and the highest point. For this graph here, we can block the graph from the bottom. There are no points below this blocker, but we can't block our graph from the top because these arrows indicate that the graph keeps going up and up and up. So for our range, let's find the lowest y value on our graph by identifying the lowest point, which is right here, and the y value of this lowest point is -4. So in interval notation, we'll list the lowest y value and we'll include it using a bracket. Then we put a comma. Now we want to list the highest y value on our graph. Let's again use this same rough sketch of the graph from the previous page to help us determine the range. Now for the range, we focus on the y-axis. What's the highest y value on our graph? Let's pick some points and examine their corresponding y values. This point here might have a y value of 8. This point over here also has a y value of 8. This point here might have a y value of 20. This point here would also have a y value of 20. This point here might have a y value of 40. This point here would also have a y value of 40. Notice, as the graph continues upward, the y values get larger and larger. The arrows indicate that our graph continues upward indefinitely, so that means our highest y value is positive infinity. And again, we'll use a parenthesis next to our infinity. So when determining the range, if you see arrows pointing upward, that means your highest y value will be infinity. Let's finish off by writing our range using set builder notation. We'll start with that general outline. Again, making sure to put a y here instead of an x since we're dealing with the range. Then we need to insert an inequality to show that our y values go from -4 to positive infinity. You might be tempted to write your range like this to show that the y values go from -4, and we're including -4, so we use the less than or equal to, and positive infinity, and we don't include infinity, so we just use a less than. This is mathematically correct, but there's a simpler inequality we could use to show that our y values are between -4 and positive infinity. We could say that our y values are greater than or equal to -4. That means the same thing, and writing it this way is a little bit simpler.